try to understand a step ahead of t-test that we have done yesterday. So again, straight away, we will try to understand why on earth do we need ANOVA when we have done T, because eventually we will, when we will do ANOVA, we will find out that this is also a test which is a difference of mean test. So when we have done T yesterday, we found out that it is a difference of mean test. So difference of means mean that two groups that we have taken, the means of those two groups, are they different from each other or not? So we just do not talk of difference between them, but we talk of, is this difference statistically significant, so that it can be called as a difference which is real difference. All right, so that is something that we have done. So today we will do an extension of T, and we will come on to something which is called as ANOVA. So again, straight away we will talk of SPSS. I have some example data, so we will try to apply ANOVA onto that data so that we can understand it. So before going ahead, what we have done yesterday perhaps made sense, and you can recall some of the things from there. So the basics of ANOVA would also be same as were the basics of T. So there is not much difference when we talk of assumptions. So we will just go on with the same assumptions of T. Here, just to reiterate, the T is something which was called as significance of or the difference of mean test. So is ANOVA. As we have done yesterday about t-test, that there is an assumption relating to t-test, and that assumption is that the variance in the two groups that we are trying to study has to be equal. Alright, so that was the assumption that we have done. So when we say that variance in the two groups has to be equal, and that is one of the most formidable assumptions of T, the same is the case with ANOVA. So when we will apply ANOVA, the same assumptions would be there. The assumption is that the variance of the different groups that we are checking difference within has to be equal. So this is the basic assumption that we will follow in T also, and we will follow in ANOVA also. So what is then difference between T and ANOVA? So now we will try to understand difference between T and ANOVA. So now let's take example of T-test, and here I will be writing ANOVA. Right? So T-test, as you have seen yesterday, that is basically between two groups. Right? So the groups yesterday we studied were male and female. If you are talking that class of 58 students, the example that we have been taking since the beginning of this course, we another example that we took yesterday was also two groups. All right, the first group was someone who were offered standard scheme. The second group was who were offered new promotional scheme. So there were two groups. So this is the similar thing that you would have noticed in the two examples that we took yesterday. Now, what happens if the groups that we are trying to study and the difference between these groups that we are trying to study are more than two? So, when you have more than two groups, all right, then you will use ANOVA. So, T is only when you have two groups, but when the groups increases, which are more than two, or we have multiple groups, then we will go for ANOVA. So, ANOVA is a short form of something which we call as analysis of variance, right? So this is short form of analysis of variance. So what we do essentially, let me try to tell this to you. T-test uses the T-statistic. I mean, if you can recall yesterday, what we have done is we can check significance level of any test by two ways. One way is to look at the value of T that we calculate from the data that we have collected, and then compare this value of t with the tabulated value of t, which is the standard value of t at any level of significance. So yesterday we talked of 95%. So if the value of t which we have calculated from our data is more than the tabulated value of t, which is the standard one, then we will reject the null hypothesis. That is something we have done, and this was one of the ways of accepting a null hypothesis or rejecting a null hypothesis, right? So the same way in ANOVA also, right? We will talk of three groups now. We will now not talk of two groups. In these three groups, we will try to check the difference between them. Alright. And let us talk of, let me pen down these things one by one so that we can understand it. So in T, I was talking of the T statistic being used. Alright. So this is T statistic. One way of checking the relevance or the significance of this T statistic is compare value of T, which is compare value of T, which is calculated from your data, with T, which is tabulated value, right? And this is how you would say that whether null hypothesis is accepted or null hypothesis is rejected. But in case of ANOVA, it is also a difference of mean test. ANOVA is short form of analysis of variance. Now you would see that here we would essentially analyze the variance of different groups, alright, in one way or another to arrive at whether there is some difference between these groups whole. So here in ANOVA, the statistic that we use is F statistic, right? So this is F statistic. So here we were using T, here we will be using F. Why F? Because F statistic is nothing but actually is a ratio of variance. Alright, so hence is the name analysis of variance. So F statistic we use. So the same way as we have done compare value of F, alright, which is data, right? So I am writing its F's, which is data and tabulated. So we would again compare the value of F's, and then we would say whether this is significantly different or not, right? So this is the difference between these two. Now we talk of something which is a null hypothesis. So null hypothesis in case of T was there is no difference between groups being studied, right? So the null hypothesis will be same in case of ANOVA also. So null hypothesis does not vary because essentially both of them are difference of mean tests, right? Difference of mean test. So if I can delete this thing, then I can make it like this, and I would say that they both are difference of mean test. So one is T, one is ANOVA, right? So T is for two groups, male and female, promotional scheme offered, promotional scheme not offered. But when we have to compare more than two groups, now suppose I want to compare someone who is a government employee, someone who is a private employee, someone who is unemployed. So if I would like to see difference between them regarding something, then actually I cannot go for T because it is only for two groups. Here I have to go for ANOVA, right? In T we use T statistic, in ANOVA we use F statistic. So as we compare tabulated value of T with data calculated value of T, the same way we will compare the value of F cell. So the null hypothesis in both the cases is there is no difference between the groups being studied. There is no difference between the groups being studied. The difference here is that here groups are 2 and here groups are more than 2. So this is the basic difference between ANOVA. There is one more thing into ANOVA, and actually this is not only one thing, but there are two or three more things also. So when we will talk of ANOVA, we will also talk of post hoc tests, right? We will also talk of post hoc tests. I will tell you what these are. We will also talk of contrast tests. And why on earth do we need these tests when actually they are not there in T? We will see when we will go ahead in ANOVA. So ANOVA is a more robust form of checking the difference between the means, right? Of more than two groups. So this is background of what ANOVA is and what T test is. So with this background, let us straightway get into analysis of variance, which is ANOVA. So I have this data with me. Now this data is of sales performance of some company. Now there is this company who essentially gave training to their employees, right? And they say that I have given sales training, which essentially is written here. Sales training is given, all right? So these are three different groups that they gave three different kinds of training. And then once they were through this training, they were actually reviewed that how their performance has been impacted by this training. So there is a training exam that was conducted, all right, and then on that, using this exam, their effectiveness of performance in sales was actually scored, or some marks were given to this effectiveness. So essentially, a marketer or whosoever who is doing this business would actually like to see at which one of these three training programs is most effective. So I will do first ANOVA. Now what does ANOVA do here is, we have to understand that there are three training programs that we are talking of. So now since we have taken this example, so we will go on with this only. No, why do we need to apply ANOVA is very basics. We are getting back to basics now. Is now suppose the mean scores of three training programs that we are talking of are little different from each other. So at the very first place, ANOVA will tell us that this difference, whatever is there, as was the case in T also, that is this difference worth considering as a difference or not. So it may be the case that if the score of training program 1 comes out to be say 20, if score of training program 2 comes out to be 21, score of training program 3 comes out to be 22. So though they are three different, but are they really different from each other? So does it make sense to select one out of these three because, or does it make sense to pick a program number 3 because score here is 23? And does it really better from program number 2 where the score was 22? So this difference of 1, is it really statistically different? So that is the first thing that ANOVA will tell us, whether this difference is statistically significant or not, as was the case in T also. So once we know that this is different, then we would say yes, effectiveness of these programs are different from each other. All right, and then we will go back to mean value of these three training programs, and we would see that which program has the maximum mean value or maximum score of training exam. And then we would say that first place we have proved it, yes, they are different from each other, they are statistically different from each other, and hence the effectiveness of them are really different from each other. So now we would see that which one is better. For that we have to get back to mean value of the different training programs. So this is how essentially we do it. Now one more thing, since you have been looking at this SPSS sheet from last maybe 3 sessions, so just let me tell you a little bit about this also. Now whenever you open a SPSS workbook, you actually come across a sheet like this. Alright, now there are two columns here, not columns specifically, there are two kind of workbooks here. So first one is variable view. You can look at the cursor here. Variable view is the place where you actually define the variables that you have in your study. All right, so as I have defined here, name will be a group, so group in which I have assigned the people. Now here I am talking of training groups, so the type will be numeric. So this group I have assigned 1 to group 1, 2 to group 2nd, 3 to group 3rd. So that is why it is penned down as numeric. Width is only 1. Width is how wide do you want it. Decimals I don't need it. Doesn't make sense to me if I say that training program number 1.00 or 1.0000. So since it is always going to be a whole number, not an integer, so it doesn't make a sense for me to come into decimals. And then is label. Label is something where you can actually describe what this question is about. So this question is about sales training groups that I have formed into. So the values we have not assigned to, and nobody stops us if we can assign values. So suppose here if you go back to data view, now this group is 1 1 1 1, then is 2 2 2 2, all right, and then is 3 3 3 3. So these are three training groups that we are talking about here. So if I can go back to variable view, and if I can write down here, let's say 1, and this is training program number 1, all right, and then 2, this is training program number 2, and then 3 becomes training program number 3. So this is how actually I can go on and do it, and hence here you will see training program. So if you go back to data view now, you would not see 1 2 or 3, but you will see training program number 1. So this fellow, which is third in our data, has gone through training program number 1 and has a score of 86.66. All right. Now this fellow has gone through training program number 2 and has a score of 80.82 in training exam. So this is how I can do it. Though I can also change it to the previous view wherein I would declick the value labels and hence I will have 1, 2, 3, 4. So if I would like to look at the labels which actually I have seen so that I can come to know what does 1 mean here, what does 2 mean here, I would actually click on to value labels and hence I will have this thing. Alright, so this is about the first variable that we were talking about. So missing values are none, columns are 19s, and alignment you can keep it right, center or whatever. And now this is the measure. Now you remember we have done scales. We were talking of nominal scales, we were talking of ordinal scales, we were talking of interval scales, and we were talking of ratio scale. So this is that scale thing. And if you can pop down this thing, then you will find three things: scale, ordinal, nominal. So as we've discussed, that scale actually represents interval and ratio both. So that is why we keep it as scale only, and ordinal nominal you know very well. So here you say that whether it is a scale thing or it is an ordinal thing or it is a nominal thing. So now we will treat it as scale thing because we have assigned values of 1, 2 and 3 into it. Alright, and we know the properties of an interval scale, that it can actually be subjected to mathematical analysis, whereas nominal scale can actually not be subjected to mathematical analysis. So let us keep it scale only, and most of the times you will find that data is recording on a scale thing only. So this is thing the same way this performance has also been defined. All right, now this is how you keep on defining. Suppose you have 100 questions in your questionnaire, then you will have 100 variables being defined onto this variable view. And this 100 variables, then if you go on to data view is where your actual data is. You have to enter the data. So here when you have to enter it, now suppose this data is of 60 only, suppose I have 61 questionnaire also. Now there is this fellow who have gone through training program number 2. I will write down 2 here, which will automatically be converted to training program number 2 because SPSS now knows 2 represents what training program number 2. Now suppose you got a score of 60. So this is how we kept on doing, and we have to keep on entering the data into our data view. So this is my data view. So this is how go into it. So let me delete it up now. Get back to our previous sheet. Alright, so this is a little bit about what SPSS is. So now we were trying to do ANOVA, which was analysis of variance, and our objective here is to see whether the 3 training programs that the employees of these organizations were subjected to are effective from each other or not. So now since we have been discussing about that whether it is T or it is ANOVA, they both are difference of mean tests, right? So as they both are difference of mean tests, so we will go to analyze and into compare means, right? The same thing that we have done yesterday. So in this, all the mean tests are available. So the popular mean tests are one sample t-test, we have done it yesterday. Independent sample t-test, we have done yesterday. Paired sample t-test, we have done yesterday. Now we will be doing one-way ANOVA. Alright, so the mean comparison tests are under the head of compare means. When compare means, we will go to ANOVA, one-way ANOVA. I am going to click onto it. I will come across to a window like this. Alright. Now I have these 2 variables only, right? So if you can go back to the sheet, you will find I have one variable which is group. I have another variable which is performance. So had you have 100 questions into your questionnaires and they were defined into the variable view, you would have looked all those 100 into this small window which is in the left hand side of this pop-up window, right? So here in ANOVA we have 2 things which you have to be very crystal clear about. These 2 things are, one is the dependent list. Dependent list is the factor which you are going to study. So here we are going to study the training effectiveness, and training effectiveness we have converted into some mathematical paradigm, and that is what my training score is. So I will get score of training exam into dependent list, so that becomes my dependent variable, right? And now sales training group, which is my factor, we have 3 groups, I will get into factor. All right, so this is something, how do we drag which thing into what thing. So now before proceeding, let me go back to our Excel, and in ANOVA we were talking of assumptions, right? So assumption is homogeneity I've clicked wrong. So there you are. So we were talking of assumptions, right? So in assumptions is homogeneity of variance. That is something that we are going to check using Levene statistic, right? Statistic. This is one assumption. Now the second assumption is it has two variable. One is dependent, all right, variable, and one is independent variable. So and independent variable, right? So its dependent variable has to be on. Now understand this carefully. Now it will be very useful when you are going to do it. Dependent variable has to be on metric scale, right? And independent variable has to be on non-metric scale, right? So which means what? Now this thing has to be a factor. Independent thing has to be a factor. Dependent thing has to be a scale variable. So here independent thing non-metric, as you also know that it is also called as categorical scale. So here we have to have some categories, right? Categorical data. So here I have a sales training program 1. So someone would have gone to 1. Now that makes one category. Someone has gone to training program number 2. So that is my second category. Nothing exists between 1 and 2. There is no one who have partially gone to 1 who has partially gone to 2 also. So 1.5 do not exist, and hence it is a non-continuous scale, and hence it is a non-metric scale, which is also called as categorical scale, right? So we have three groups here and they are actually non-metric. So metric thing would be that which is continuous. So the score that we have given in our training exam is basically metric thing, because if you can look at this thing, a score of 65.53 is possible. Continuous scale, also called as metric scale, also called as non-categorical scale. All right, so this is that assumption that we were talking about. So we will have two variables, dependent and independent. One has to be metric, one has to be non-metric. All right, so non-metric will be my factor variable when I do it in SPSS. So this is my factor thing. All right, so this is non-metric thing. Sales training groups, I have three groups, and here independent list I will keep up something which is onto metric scale, the dependent thing, the thing which actually I am trying to measure everything for. So here my thing is training program or training exam result. All right, so now having dragged these two things into my analysis window, I will then click on to options. All right, so I'm just rerunning through what I have done. I've gone into analysis, compare means, then I've gone to ANOVA, right? And then I have dragged sales training groups into factor and score on training exam into dependent list. Then I've gone into option and I will click on to descriptives. All right, important to do. We know, we have discussed it multiple times, there is assumption in ANOVA, assumption of analysis of variance test. I've highlighted it with yellow. So this is to be checked. So to check it, we have to click on to homogeneity of variance test. So let us do it and check it. All right. So then you say continue, right? And you say okay. The moment you say okay, you will have a window before you, which is an output window. All right. Now something beautiful happens here. You see this, the descriptive check that we have done onto ANOVA. So if I can go back to my analysis thing, and if I can go to compare means into one way ANOVA and into options, right? So I'll just drag it down into options. You will see I've checked onto this descriptive things. This is output of this. All right, so this is descriptive that I have checked is here. So now another thing which I have checked is homogeneity of variance test. So there you can see test of homogeneity of variance, right? And then as I have clicked on to OK, and as this OK was for one way ANOVA, so I have got a ANOVA table also, right? So this is something what has essentially happened, and this is an output window of SPSS. Now one more beautiful thing that I would like to tell you about SPSS, that these tables which SPSS generates, all right, tables which SPSS generates are not normal table, but they are pivot tables. So you must have heard about pivot table in Excel also. So all these tables are pivot tables, which means they are active tables. You can anytime convert the rows into columns or columns into rows or whatever. All right. So for example, if I have this window before me, which is a descriptive window, I can click onto it and I can actually open, right? And click onto these things. These are something before me. Now I will go into and I will go into pivoting trace. So I have this thing before me. So you look at now, if I get this row, it represents a row. Now you see it is changing there, right? If I can get this row thing into column, now see this changes. So if I can get this column into rows, this changes. So you can change anything. So I will drag it back to the normal position where it was, and I'm just making rows as rows and columns, and I'm out of it. Right? So these all are pivot tables. You can change them anytime. So now come back to ANOVA. Now this N represents the number of people. So the training program number 1 has 20, training program number 2 has 20, training program number 3 also has 20. So the total number of people that we are evaluating today are 60. This is their mean. We can actually see that training program 1 number has a score of 63.57. This is my training exam score. Training program number 2 has a score of 73.56. Training program number 3 has a score of 79.27. So this is the total overall mean of 60 people, and this is the group means. Again, as we have been doing since beginning, that on the face value they looks different from each other. So 63 obviously is different from 73. So 73 obviously is different from 79. But having said that, does this difference of 10, which is 63 to 73, is actually different? Does the difference of 73 to 79, which is 6, is it actually different? So if we take difference between group number 1 and group number 3, which is 63 to 79, now that is huge, which is 16, is it really different? So that is something that ANOVA will tell us. So this all the things are same that were in the case of t-test also. So this descriptives tells us about some wonderful things which can actually be very important for us to know. Now have a look at the variability in group number 1. So when we say that mean is 63, so the standard deviation is 13. So it's a huge standard deviation when we are talking about, because there are many people in this group which are 20 which also has a mean score of 76, because 63 plus 13, which is the standard deviation, this is the variance, this is the variability from the mean. All right, so when we talk of these number of people having a mean score of 76 here, so you look at now these people who are having 76 exam score and are in group number 1 are actually not more different from the training program number 2, training program number 3 also. And that is why it is important to have a look at standard deviation. I tell you once again, this mean value of 63 is obviously different from 76 and is obviously different from 79, but you do not forget the standard deviation is 13. So 13 standard deviation would mean that there are some people out of this 20 in training program number 1 who has got a score of 76 also, right? So I do not know how many people have got 76, but since standard deviation is 13, I can easily guess that there are some people. And when I talk of those people who got a score of 76, they are not much different from training program number 2, training program number 3. And essentially, they are really not much different from training program number 3 because standard deviation is very low here. So this group has the people ranging from 75 to 83, which is the score. So a score of 76 is not much different from 75. So maybe 1 and 3 groups are closer to each other because 1 has a large standard deviation and 3 has small standard deviation. So this is how it is important for us to understand the importance of standard deviation while calculating the results, and that is precisely one of the examples which essentially tells us that we cannot conclude by just looking at the mean scores. All right, so now getting ahead. Now this is our test of homogeneity of variance. in test of homogeneity of variance, we can see is Levene statistic. So if I can go back here, so this is homogeneity of variance, which is a Levene statistic test. So let me get back. Here is your Levene statistic. So if you can recall, yesterday we have done the null hypothesis of Levene statistic, and null hypothesis for Levene statistic was there is no difference between the variance of the groups. All right. So since the value of this significance, which is p-value, is less than 0.05, what does it mean? Now I would like you to tell me a value of significance which is less than 0.05 in Levene statistic. What does it tell you, Manjula and Rajat? Please tell me. A value of p which is 0.01, obviously which is less than 0.05, what does it tell us? Should I conclude that the variance of these three groups are different from each other? Or should I conclude that the variance of these three groups are not different from each other? I'm waiting for a response. What do you say? Levene statistic we are up with a p-value of 0.01 as the case is. What does it tell us? Manjula and Rajat would like to attempt it? I hope no. So let me go ahead with it. What does it actually mean? So I am here on to SPSS output again, and this thing, a value which is less than 0.05 would mean that null hypothesis is rejected, and when null hypothesis is rejected, it means that the variance of these three groups are actually different, right? So this is something that we are coming up at now. So since the variance of these three groups are different from each other, the assumption of homogeneity of variance means the variance has to be equal across the groups is not met, right? So this assumption has actually been not followed by this data, at least in these three groups. So when it is not followed, then in ANOVA we cannot go with F, because if you look back here, ANOVA uses F statistic, right? So but when this assumption is not met, then F tends to give us highly exemplified results. Either it is too high or either it is too low, because F is nothing but is a ratio variance test. So when this thing says that this variance is not equal, I cannot go with F, right? So that means what? That means that this value of significance which is less than 0.05 does not convey anything to us, and if at all it is conveying anything, then that is not important to us, right? This is essentially what we are talking of now. Now what to do in such cases when assumption of homogeneity of variance is not met? We cannot go with that. In such cases, we have to go with some robust tests of checking the difference in the means of various groups that are being studied, right? So I'm just writing it down. So we have to go and do robust test. So this is something which will come here. Robust test, right, of mean differences. So this is something that we are coming about now. So as this is not done, so I will take help of robust tests. So again I will go back to analyze. I'll go to click compare means and we'll go to ANOVA. So everything is at its place now. I just have to go to options, and here I will click on to Brown, Forsyth and Welch. Now these two tests, in fact they are three in number, because Brown is a different test, Forsyth is a different test, and Welch is a different test. So these three tests are actually called as robust test of equality of means, right? And now I will click onto it and I will say okay. So you will have another output of ANOVA, so that doesn't look too different from what we had earlier. But there is some addition to it, and that addition is a robust test of equality of means. Now that is what we have added because we found Levene statistic to be significant, and hence I cannot go with F. I have to go for some robust test of difference of means. And in this robust test, now we would look at Welch and Brown-Forsyth, right? So now here significance value is 0.000. In Brown-Forsyth also the significance value is 0.000. So what does it tell us? It tells us that the difference between these three groups, or the difference between the means of these three groups, are actually different from each other. Alright, are actually different from each other. So this is something that we will conclude. So the same way as we would have done it with ANOVA also, we will just not look at this significance value of F because assumption of F is not satisfied. So these two statistics, which are Welch and Brown-Forsyth, actually are robust to the assumption of equality of variance across the groups, right? And hence the significance value which is given by them will actually be the real test value. So now we will believe onto this significance value but not this one. Though the differences are not much, though both of these are saying same thing, looking at ANOVA also significance value is less than 0.05, which essentially tells us that the difference between these three groups is actually significant. The same story is told to us by these robust tests, which tells us the difference between these two groups is actually a statistical difference, right? So now, one more thing which is important to note here is that many times it so happens when Levene give you a statistically significant result, which means that variance across the groups are not equal, and hence you cannot go with F. Now you have to go for robust test of equality of means, which are Welch and Brown-Forsyth, right? In Welch and Brown-Forsyth also, many times you will find that Welch is giving you a different result, Brown-Forsyth is giving you a different result. What do I mean by that is, if Welch is giving you 0.000, and had it been the case that Brown-Forsyth would have given you a significance value of 0.276, suppose, so now that would have meant that these two tests are actually telling us a different story. So if I can take it back to our Excel, now this is essentially that we are trying to understand. So I've copied it. So now let's take this thing here and let's convert it into a number, right? So here it is 0.0. Increase the decimal points to 3. Now I am talking of a case where this thing would have been like this. So this thing would have been like 0.276. Alright. So what would have that meant? Now Welch is giving me a different story. Now this story is a story of statistically different result. Brown-Forsyth is giving me a different story, which is giving me a value of 0.276. Now that means that this Brown-Forsyth tells us that there is no difference, right? There is no difference between the groups that we are studying. Now, which result to believe? In such cases, when there is a conflict between Welch and Brown-Forsyth, you will go with Welch because Welch is considered to be more robust than Brown and Forsyth. So Welch will give you a green signal and you will go ahead with Welch and you will delete the case of Brown-Forsyth in case if they both tends to give you different results. So this is somewhat red, this is somewhat green. But that is only the case when you have these two statistics giving you different results, right? Now, any problems to this point? So I hope we should go ahead. So here you are. So now we will be trying to do and trying to look at one more very important assumption, and that assumption is of this thing. Now this homogeneity of variance that we are talking about, right? Homogeneity of variance, I am just copying it here. There is an exception to it. There is an exception to it. So I'm talking of this exception of homogeneity of variance test. And what is this exception? Exception is when the various groups under study are of equal size, then this assumption can be overlooked, right? So this is something that we are arriving at now. So what we are saying here is that we actually have to overlook this assumption if the sizes of the groups are equal. So if I can go back to our analysis, now getting back to descriptives, we have 20, we have 20, we have 20. So the three groups that we are talking about are of equal sizes. So when they are of equal size, we may believe on to F. This is an assumption, this is an exception to the assumption, and we must remember it. When the group sizes are equal, we need not to go for robust test of equality of means, because when sizes are equal, then ANOVA itself, which is F, so the F itself is robust to the violation of homogeneity of variance, right? So I'm just repeating it what I have just said. What I have said is that when your group sizes are equal, right, then the assumption that we have talked about, that there should be similar variance across the groups that we are trying to study, right, that assumption actually does not hold true, or F actually is robust, F itself is robust to that assumption if the group sizes are equal, which is 20, 20 and 20. Had it been the case that this 20 would be here in program number 1, 30 would be here in program number 2, and 25 would have been here in program number 3, which means n would have been different. In that case, we would not have looked at F, but we would have actually looked at Welch and Brown-Forsyth, right? So this is that assumption. So if we can take another example, now let us take this wait time thing here, so which actually will give us an example where the group sizes are unequal. So wait times in minute. Now this is essentially a data recorded for the wait time in different branches of a bank. So we have various branches of a bank. If I can go back and see to it, then you will find that this is bank branch, and bank branch are actually three which are being studied. So one is branch A, two is branch B, three is branch C, and this is essentially the wait time in minutes at each branch. So now here what we are trying to study is that is the wait time in three different branches of the same bank different from each other, and not only different, is statistically different from each other, and if it is, then which branch is more effective, or which branch is capable of providing the services with minimum wait time. So now let us go back to our analyze, and let us go back to compare means, and let us go to ANOVA. So here wait times in minute is my dependent list. So if you can recall, my dependent list should be at metric scale. So metric scale would mean that it is a continuous scale. So a value of 1.25 is also possible, right? So that is why wait time has been taken as a dependent list, because wait time is in minutes. It can be 1.25 minutes, it can be 5.1 minutes. So then bank branch, which is a categorical variable, is taken into factor. So we have three branches: branch A, branch B, branch C. So these are three different categories that we will talk of, and there is nothing between branch A and branch B. So if I give 1 to branch A, if I give 2 to branch B, there is nothing between branch A and branch B. A value of 1.5 is not possible. So that is why it is a categorical variable, right? So now I will go back to options, as I have gone there also. So I'll click on to homogeneity of variance test. I'll click on to descriptives, continue, and say okay, right? So here you look now. In branch A we have 125. In branch B we have 90 people. In branch C we have reviewed 100 people, and this is their mean times. So mean wait time at branch A is 5.5, mean wait time at branch B is 5.2, mean wait time at branch C is 5.1. With standard deviation of branch B and C being lower than 1, with mean time of branch A being little higher than 1, standard deviation is not much here, but a standard deviation of more than 1 at a scale of, when you're talking of only 5 minutes, is actually can be considered as a good variance or a good standard deviation. So here the reason that we took this example was, have a look at this n. Now here n's are not equal. So branch A has 125 people, branch B has 90 people, and branch C has 100 people. So in earlier example that we took, the number of people that we were talking about were equal. They were 20, 20, and 20. Here we have 125, 90, and 100. Right? So when this n is different, we cannot overlook this thing here. All right. So this test of homogeneity of variance we have to look at, and now this gives us a significant value which is less than 0.05. That tells us that the variance in these three branches is not equal, is statistically different, and is not by chance. So when this is the case, we will not go for F now for sure. So we are not going to believe onto what F says, not at all. So in that case, we will surely go for one-way ANOVA, and in options we will click on to Brown, Forsythe and Welch, and I will say continue and press OK. So I will have another ANOVA being run for me, and now I would look at this thing, robust test instead of this F. Now the prime example before us is now these two, Welch and Brown Forsythe, they are giving me different significance figures. So if I can go back to my Excel, now this is the example that we took, that if these two are giving you different results, Welch is giving a significant result, Brown Forsythe is giving you non-significant result. Now here is the practical example before us which is actually telling us this story. So Welch is giving us non-significant result because it is more than 0.05. Brown Forsythe is giving us a significant result because it is less than 0.05. So Brown Forsythe says that these three branches, whatever the wait time is, that can be treated as statistically different from each other. Alright, whereas Welch tells us that the wait time across these three branches cannot be treated as a different time, because statistically we do not say that 5.1 is different from 5.2 considering this data set. So 5.2 is not different from 5.5, or 5.1 is not different from 5.5. Right? So this is what these two things are saying. So which one to believe now? If I go with Welch, I would say that we should not treat this difference as to be something which is a considerable difference. But Brown Forsythe says that we should treat them as a considerable difference, having looked at the data set that we have infused or injected into ANOVA. So in those cases, as has already been mentioned, Welch is in green, which means we have to, in case of conflict between Welch and Brown Forsythe, we have to believe onto Welch but not onto Brown Forsythe. Alright, so Welch would be yes and Brown Forsythe would be no. So here, if you would look at, we will go for Welch, and Welch says that this difference should not be considered as significant difference. So the inference that we will draw out of it is that these three branches are not much different from each other as far as waiting time is concerned. So all the branches are on an average at same waiting time, but no one is different from each other, right? So if we can go back to our previous example that we were trying to do the sales performance story, right? So if we have to interpret the results of this, now let me get back. Compare means convey ANOVA and score of training exam. Let me drag it to dependent list, sales training groups into the factor list, options, descriptives, homogeneity of variance, Brown, Forsyth and Welch, continue and OK. And here I have this thing now. So since this size is equal, now this is of no use to me. So I can actually delete this thing. I don't need it. So when this size group is equal, I also do not require robust test. So I will also select it and I also delete it. So now this is the full ANOVA to me in these specific conditions, right? So what I would infer out of it is that significantly these three groups are different from each other. Alright, so whatever is the difference between the sales performance of the group which has gone through the training program number 1 is actually different from training program number 2 or 3. That is something that we will infer out of it. And now we will look at the scores, which are mean scores. We would say that 79.27 is the highest score that one has got, and that is of the people who were in group number 3, right? Then we would say that the training program number 3 was most effective in producing the results. And moreover, we should not also overlook the fact that this training program has minimum standard deviation. So which means that most of the people are actually clubbing around the mean value, or they are not much far away from 79. So the only difference that we would say is that the range here would be 83 to 75. So 75 to 83 is what most of the people are getting. Or we would say, if you can go back to our normality, if you go back to our normal distribution, then what does it tells us? All right, what does it tells us is, if I have to take you little bit back in normal distribution, we said in normal distribution we said that when z is equal to 1, it actually roughly takes 65% of the population. When z is equal to 2, it roughly takes 95%, right? So this is 95% actually. So here, and what is z? Z is nothing but the number of standard deviations away. So if we can look back at this output, we would find that standard deviation is 4.4 and mean is 79. So let's take them in whole value just to make calculations easier. So 79 is mean, 4 is standard deviation. So our 79 is mean and 4 is standard deviation. So this is ST, this is mean, right? So this is mean. Now, what does it mean? It means that range that we are talking of, minimum and maximum. So, range would be 79 minus 4, right? And 79 plus 4. Of this range from 75 to 83, there would be almost 68% of the people. So which means what? That we were having 20 people in this group. All right. So this 20 group, what is 68% of 20? So 20 multiplied by 68, right? So we would say that almost 13 people would have a training exam score between 75 to 83. So this is how we tend to do it. And as the standard deviation is low, we would say that this is the most effective method of giving training. All right. So this is something about one-way ANOVA. Now some more technicalities about one-way ANOVA is left. we would like to carry it on in our next session. All right. So this is from me about one way ANOVA. So if you have any questions, Rajat, then you may please ask.